Hi, my name is Stalin Ibanez, and I would like to welcome you to the presentation of a numerical approach for plastic cross-sectional analysis of steel members. This project has been developed in cooperation with Professor Matthias Kraus at the Bauhaus Universität Weimar. The motivation of this work comes from the field of civil engineering, in which normally we use beam element for defining big structure and for performing normal calculations daily. Why do we do that? Because it's simpler in the terms of defining the structure, and also it's faster when we want to perform the calculations. If, for example, we would like to do the same using shell element or volume element, we would find difficulties in defining the boundary condition as the support and the application of the loading. However, there are some limitations with the beam elements when we want to perform more complex calculations. The problem of analyzing more complex cases, for example material nonlinearities using beam elements, has been addressed before by Kraus and Kidman. In their work, what they do is that they combine beam elements with the cross-sectional analysis, in which they define the cross-section with small fibers. For every fiber, they calculate the shear and the actual stress of the current load state. Then, for verifying if the stress level is the one that corresponds to the material behavior that they define at the beginning, what they do is that they do not combine these stresses, but they reduce the yielding capacity of the material by considering the shear stresses. Then the actual stresses are verified according to this reduced yielding capacity. In the current work, what we want to do is to improve this a little bit and considering these two stress components combined by certain criteria, and then to verify this against the material properties. Before going into the implementation of the algorithm, the plastic analysis, I would like to review three main conditions that should be fulfilled when we do any plastic analysis. The first one is the yield condition. In the yield condition, what we do is that we ensure that the current stress state is always inside of the surface, the yielding surface. That means that the stresses, the combined stresses, cannot be bigger or outside of this surface. If they are, they have to be corrected. The second rule is the hardening rule, in which the yielding capacity is somehow updated every time that we have some plastic strain. And that means that we have somehow a kind of memory in the fiber that we are analyzing. This is represented here by this dashed line in which the stresses, the capacity of the stresses somehow are increased. And the last rule is the flow rule, in which we define that the direction of the plastic stresses are going to be always perpendicular to the yielding surface. By combining the three rules described before, we can reach the elastoplastic constitutive relationship, in which the strain are related with the stresses with the corresponding equation that we have here. Here we have the elastic constitutive relationship, which is somehow reduced by this part of the equation that represents the plastic state. This algorithm is implemented in the cross-section by defining the cross-section by line elements. These line elements are divided into small fibers, and in each fiber we will evaluate the current strain state, and with this strain state we will calculate the corresponding stresses. The formulation can be expressed specifically for the stress field of beam theory. That means that we consider the stresses that we normally have in the beams. This is the actual stress sigma x, and the shear stresses tau xy and tau xz. Also, these two stresses can be represented as just one stress following the direction of the line element that we have in the cross section. The yield condition here can be expressed by the von Mises criterion of the equivalent stresses, and also the hardening is represented by the yielding capacity plus the plastic strain multiplied by this relationship H that exists between the tangent modulus and the elastic modulus. Finally, the flow rule, when we replace all the terms, it looks like this. Also, the elastoplastic constitutive relationship in which we have the elastic part and we discount this somehow plastic part. The plastic part is going to be represented by this matrix of 3 by 3 in which we have the corresponding components of the beam element stresses. And you can see here how the stresses influence the behavior of this elastoplastic relationship. Here I would like to present the algorithm for this plastic analysis. We have the cross-section, and for the cross-section we are going to apply a certain increment of loading. This increment of loading is going to produce an increment of strain in the fiber that we want to analyze. For every fiber, we are going to run this plastic algorithm. In the fiber, we will have certain increment of strains, and this increment of strain, we will use it for determining the strains at the step I. Also, the stresses will be determined with these corresponding strains, and the stress at the step I is going to be updated. We call it trial stress because we want to test if this is the real stress state or not. We apply the yield condition. If the yield condition is fulfilled, then we can move to the next step. If not, then we have to correct the stresses. For correcting the stresses, we have to calculate the corresponding plastic strain at the current level of stress and to update the hardening of the material also for the current stress level. With this plastic strain level, we can calculate the corrector of the stresses. When the stresses are outside of the yielding surface, we can bring back the stresses to the yield surface by calculating this corrector. We check the stresses, the trial stresses that we define, we correct them, and then we put that again into the yield condition. If this is not fulfilled, we have to repeat the step. If this is fulfilled, then we can move to the next step, in which, again, the increment of strain will come from the increment of loading in the cross-section. This algorithm has been tested first for validation. That means that we compare the result that we obtain with a commercial software, in this case ANSYS. And what we did was to extract, to model a structure in ANSYS and to extract the stresses from this structure and to put that as an input in the plastic algorithm to check if the development of the stresses is correct. As you can see, for pure bending and pure shear, these work perfectly. And in the case of combined stresses, when we have a strain, shear strains, and also axial strains, the algorithm works with certain differences in the actual stress in this case. This is explained by the fact that in ANSYS, the model that we had considered more stresses than this simplified method with two stress components. The algorithm has been tested for different loading cases, and the material properties that we are using are the next one, in which we're mentioning that the tangent modulus is 100 of the elasticity modulus. For the case of pure bending, we apply a bending loading in the cross section, and we can see here the elastic distribution, which is something that we would expect with the higher values of stresses in the upper and lower flange. And when we increase further the load level, we see how the plasticization starts from the upper and lower part of the web to the center of the web. We can also notice here that in the upper and lower flange, the yielding capacity has been increased according to the hardening rule that we have defined. In the case of pure shear, we applied a shear load here in the profile in the direction Z or in the vertical direction, and we see here how the stresses are maximum in the center of the web. Again, when we increase the loading, we see how the stress level increases up to the upper and lower part of the web and also to the flanges. When we analyze a combined loading condition, for example, in this case, a higher bending loading, we can see how the stresses distribute differently than in the previous pure cases. For example, in the case of the axial stresses, previously for pure bending we have a linear distribution. Now this distribution follows a nonlinear path. This is due to the contribution of the shear stresses in the web as well. Also here in the midpoint, we see now how the shear stresses are the main contribution to the plasticization of the section. Here you can see the equivalent stresses of the whole section, in which every part of the whole section is plasticized. When we take just one specific point of the section, for example, this fiber here in the upper side of the web, we can analyze how the stress path looks like with respect to the shear stresses and the axial stresses. We see how when we reach plasticization, the stresses somehow accommodates a bit along the yielding surface, and then they start to increase again up to the next step in the hardening part of the yielding. Following with a further example of combined loading, in which now the shear loading is higher than the bending, we see now again how the actual stresses looks linearly in comparison to the previous case, because here the major contribution of the stress state comes from the shear stresses. We can also see how in the upper flanges the stress contribution from the side of the actual stresses is not that higher in the midpoint, but it is higher in the extreme point of the flanges, and this comes from the contribution of the shear stress as well. And here we see the equivalent stresses of the full section. Again, we can take just one fiber and analyze how the path of the stresses looks like, and we see again some accommodation of the stresses in the yielding surface up to a certain point in which we can continue increasing the yielding surface. So as a summary, the plastic formulation has been implemented for the specific case of two stress components, shear and axial stresses. The algorithm has been developed and implemented for elastoplastic analysis in the cross-section, and this has been validated in comparison to commercial software. More tests has been done considering different load cases in which we have higher shear, higher bending, or pure shear and pure bending, and the algorithm works properly. Further research will focus on implementing this in the cross-section, but considering isoparametric element in the cross-section to see how the stresses change. Thank you very much for your attention, and I'm here for any question.